Okay, let's get started. So, are you set? Okay, so I sent an email about my office hours saying I need to move it by an hour. So if you are planning to come see me today, I will start my office hours at 5 and not at 4. If that poses any problem, email me. I can see if there's some other time I can talk to you. Okay? All right. So let's get started. I just now I got a request to explain total order multicast again. I will see if I can put up an example on how it works if some of you are still confused. Because I can explain it next time with an example, but it will be too late for the lab. Okay, so let me do that separately from the lecture. So just to recap, last time we talked about leader election and distributed locking. Today we are going to talk about distributed transactions. Okay, and then we'll talk about consistency and other things next time. So first of all, are there any questions on either leader election or mutual exclusion? There's from the Piazza post, we see that some people don't seem to have understood what leader election exactly does, how not what it does, but how it should be implemented and so on. So if there are any questions, you may ask so that I can clarify before the lab is due next week. Yes?
So in leader election, like for our lab, we have our dispatcher server, it's multi-tier. So should we, when we're electing a leader, is that all the servers, all 4 of them, like dispatchers,
right. So question is, for leader election, should you include the dispatcher process? That is completely up to you. It doesn't matter one way or another. At the very least, you should include the 2 front-end servers and the back-end process, at least 3 of them. You can also include the dispatcher as a 4th node and make it the leader, because the leader election is only used for time synchronization, right? Clock synchronization. So you can have 4 processes participate as well in that. Okay. There are some questions about clock synchronization, whether it's done one time or periodically. Like any clock synchronization algorithm, it goes without saying that every so often you need to resync the clock. Okay. So your technique needs to actually do it more than once, not just do it at the beginning and stop doing it and things like that. Yes.
And so for that, we would assume our own deviation.
You can make some assumption about deviation. Just show it happening every so often, and that is adequate. Okay. Any other questions? Yes.
So in leader election, if we include the dispatcher and we give it like say the highest ID, and so the leader election algorithm doesn't really achieve anything in this case, right? Because each time the dispatcher ends up being the leader, and you're not really.
Yeah. So you can. So question is, if you give the highest ID to a process and it initiates the leader election, there's no reason it has to initiate the leader. So you can give the dispatcher the highest ID or any process the highest ID just to show that the leader election works. Have some other process initiate the leader election. Right? The other thing you must show is there are no failures in this lab. So none of the processes fail. Fault tolerance is lab 3. Having said that, so you don't have to worry about failures for the purpose of leader election. But at the very least, you can show maybe the leader resigns or something, and then you elect a new leader with the remaining set. Some cooked up example that shows that the leader election is supposed to work as, but you don't have to deal with failures or anything like that. Okay, so it's much simpler. But you have to at least show that your code is exercised properly by having the leader election be initiated by a few different processes, or the leaders stepping down and electing a new leader. So that's how these techniques are supposed to work. Yes.
For fault and for giving up the leadership, can we just since we are running on 6 clients or something, or 6 servers replicated, or whatever, 3 servers or something, we intentionally kill a server, just like.
Yeah. So you don't have to do actual faults. You can do that. That's actually supposed to be lab 3. Okay. So you can certainly terminate a server, but then you will have to deal with all the clients that were connected to it. They have to fail over. So there's a lot more that has to happen, not just the failure of a leader. Right. So you could do that, but I think it is much easier if you just say I resign and assume that it is not there.
Okay.
That's the simulated version. It's much easier to do. Yes, question.
Do we have to assume that all the servers are owned by initiating the leader election? Or
All the servers are what is the question?
Like all servers are up in the system.
Yes, so question is, should you assume all the servers are up? Yeah, you can start the leader election after all the servers come up and assume that they stay up. There is no failures of servers for leader
Can
election.
we consider the case like any of the server is joining the system in between?
Right, so in this case, again, we don't have dynamic joins, leaves, you don't have faults. So you don't have to consider a case where new server shows up or anything like that. Having said that, just to exercise your leader election, if you actually have the current leader step down and not participate, and then the rest of them elect a new leader among the remaining, that's good enough. That's all you need to do.
So are we safe to assume that there is only 2 intermediate servers and the dispatcher can just maintain the 2 of them, or will more servers, intermediate servers be added?
Okay, so question is, will there be more intermediate servers added? So your code should be able to handle replication across more than 2 front-end servers. Having said so, you shouldn't hard code things that it only works for 2 but not for 3. That's very easy, so long as you don't make some bad assumptions, it should scale easily. So, but you don't have to show more than 2 necessarily for all of this leader election and things like that. Okay. Yes.
And do we have to? Can we use REST APIs for the sake of leader election, or should you have to do it using sockets?
Okay, question is, should you use REST API or sockets for leader election? So notice that we did not specify any APIs beyond what was there in lab 1. So what should you use between the front-end server and the database server? What should you use for leader election? That is your choice, design choice. Having said that, it is straightforward to simply extend your HTTP API to have some more calls saying elect a leader, or even run clock synchronization through it. That way everything is uniform. You don't have to have part of the code using RPCs, part of the code doing something else. Okay, you are certainly welcome to use the same thing between the front-end server and the database server, or you can use Pyro, which is Python remote objects, or sockets if you so wish. That is completely left to you, but if you want to simplify it, keep it the same. Okay. Any other questions? Yes.
For the clock synchronization, should we artificially like fake time drift between the different servers?
Okay. Question is, do you have to fake a time drift? You don't have to go that far, but you can assume a worst case time drift, which will simply say then the clock synchronization has to occur every 4.5 minutes based on the delta over 2 row. So you can make those assumptions, but the clock doesn't actually have to drift. That's just the worst case drift that says I have to synchronize every so often.
So the offset being 0 doesn't matter?
Offset being 0 should not matter, although if you actually look at it at millisecond or nanosecond time scale, it should not be 0.
Okay.
At second resolution, most likely it will end up being 0. So just see if you can do a little more fine-grained version of time, clock time, and then you should hopefully get a non-zero offset. Okay? But if it comes out 0, so be it. Any other questions? Yes.
So, like in the Christian server, we actually consider the time taken by if we the time taken to travel the time from one server to the another. So do we have to take that particular consideration?
Yeah. The question is, should you take network propagation delays in clock synchronization? Absolutely. Otherwise, there's nothing left to do. Right? Just taking 2 clock values and taking the average is not really clock synchronization. There's no point there. You have to. That's the whole point of the clock synchronization. How can you estimate network propagation times? All right. Yes.
So for the dispatcher to work, should we hard code the servers, the intermediate servers that we use, or like if you want a dynamic join, we need it to write to a file or something like that, right? Or a database.
Yeah, so you can actually have dispatchers built any way you want. You can have it to handle more than 2 front-end servers, although you have to show only 2. You can have a replication happening dynamically. That's going to come in lab 3. So if you make it a little more flexible now, you will benefit in lab 3. If you do the simple thing, you'll have to do a little more work in lab 3. And you can certainly use config files to do whatever you need to do. Okay? The only thing I'll mention again is the dispatcher doesn't have to do request level load balancing. It is actually doing client level load balancing, which is simpler. So whenever a client joins, the dispatcher will assign that client, or rather the client session, to one of the, in this case, 2 front-end servers. From that point on, all client requests only go to that client. That's how session level load balancing works. Okay. So it's not that every time a request comes, you have to figure out the load and try to send it to one of the front-end server. It's only when a new client comes, you have to do that. Okay? That means that when there are no new clients, the load on the two front-end servers won't necessarily be balanced if the request rates are not identical. But that's how session-level load balancing works. Okay? So you're only assigning clients to front-end servers, not individual requests of the clients. Yes?
Building off of that, are we allowed to have the client initiate their log out from the session, or do we have to do like a timeout?
What do you mean by log out?
Like, so if we're doing load balancing and if we have a client starting a session, when the only way for that load to decrease for that server is if the client leaves. And so is it okay if we have the client initiate that? So
Yes, you can certainly say I'm going to leave if you want to do it that way, or you can just introduce new clients in the system
Okay.
just to test out your load balancing. That's also fine. Okay. Any other? There was some question. Yes.
So for the dispatcher, when a client comes in, it sends it to the dispatcher. The dispatcher sends the server address, and then the client directly talks to the server.
Right.
Is that how it works?
So there are two ways to implement the dispatcher. The first approach is what is mentioned here, where you go to the dispatcher and say which front-end server should I use, and it will tell you one of the two in this case, and from that point on you send all your requests to the dispatcher. That's a simple approach and a better approach. The other approach is the dispatcher is in line for all your requests, which means that the first time you send a request, it will automatically assign you to one of the front-end nodes without telling you. You just keep sending your request to the dispatcher, it sends it to whatever server has been assigned. Okay? In that case, it's actually in the data path. All the requests are flowing through the dispatcher. The first case, it was only in the control path. It was only asked it, and then all the data flowed directly to the server. Both of those are fine. Okay, you can do either. The first one is obviously simpler to do, so you can pick that approach. Okay, both of them actually are used in web cluster, so in this case, we'll allow either. All right. Okay, so feel free to ask questions or Piazza. There's no class between now and actually there is a class on Monday because you can come on Monday, although that may be too late to ask questions, but you can always stop by at office hours and whatnot. All right. So last question was any comments on the exam before I start the lecture? How did it go? Long. Okay. Okay, that's not that bad at least. Just have to write a little more. Okay, so we will start grading. We'll have the feedback in about 7 to 10 days time. We haven't started yet. All right, so let's get back to the class lecture. We will talk about distributed transactions today. Okay, so we'll pick from where we left off last time, which was distributed mutual exclusion, and talk about transactions. So you probably have heard of transactions in the context of databases. Okay, so they're actually widely used in most of these relational database systems. I will introduce that concept again to you if you're not familiar with it, and then we are really going to talk about distributed transactions. But to understand distributed transactions, you need to know what transactions are. Okay? So transactions at a very high level provide you a mechanism that gives you this notion of atomicity, which means any operations that are performed inside a transaction have all or nothing property, which means they all execute successfully, or none of those instructions execute successfully. Okay, that's called atomicity. Okay, so you can have a transaction that has a set of bunch of code, and the transaction will guarantee you that it will all execute or nothing will execute. So even if the process crashes in the middle of the transaction, you're supposed to undo whatever has happened so far, so it look like nothing has happened, which means you get the nothing property. All of it does happen. So those are the basic properties that the transactions give us. And I'm going to show you some examples of why you need it to begin with. Okay, here you have a database, a simple database that's, let's say, a banking database, and you have two examples, or not two examples, there are two clients that are performing operations on the database. Okay, and the client one wants to transfer $4 from account A to account B. Okay, client 2 wants to transfer $3 from account C to account B. Okay, and the way this code is going to work is you are going to read the account A balance from the database, deduct $4, read account B, and add $4. Okay, and the same thing you're going to do here. You're going to read the account balance, okay, deduct, read the new account balance, and add. And that's what you will see here. So you'll say you're reading A, You're then writing A by deducting the amount, and you're reading B, writing B, and so on. Okay, so now if you did not have any transactions or even notions of locks, these reads and write operations are going to get interleaved in an arbitrary order depending on how your application or those queries got scheduled by the operating system. Okay? So what is shown here is one interleaving, and interleaving is simply an order in which they execute. Okay, they are interleaved with one another, and that's an order. So here that's your vertical axis this time, and each time step it shows which of those statements execute. Okay, so you will read A and you will deduct $4 from it. You're going to read C, deduct $3 from there. Okay? Now client A, let's say, reads B. Okay? And now let's say the client, because its time slice expires or whatever, gets swapped out, and then you start executing client 2 here. Okay, that's going to read, and you get still $200. You add your $3 to it, and then client 1 continues execution. Is already read B. It doesn't know it has changed in the system. Because it read, it's simply continuing to execute, and it's basically written balance that's 204, and you will realize that's wrong because you're actually adding 3 and 4, so your balance should be 207 because two clients are transferred money to a common account. Yeah, and so here you have basically overwritten data, and the problem is you did not use locks. You're reading shared data and writing shared data. You don't use locks. You overwrite each other's results, and you get inconsistencies. Okay? So all transactions will internally use locks, but they simplify locks for you by just allowing you to take all those 4 instructions and just putting a begin transaction and an end transaction around those 4 instructions. Okay, and then automatically the system will acquire locks for you and make them execute in a way that they all execute at once. Okay, and while nothing else is executing, that's the illusion you get. So you should get correct results if you actually use transactions. But if you don't use locks or don't use transactions, you're going to get problems on this side. Okay, that's a very simple motivation for why you need transactions in databases. Okay. Now there are more properties. So this is what it should look like. If you actually use a lock or a transaction, you will have client 1 essentially, in this case, has gotten a lock on A and B, and then client 2 has gotten lock on C and B later. So all these 4 execute first, all those 4 execute next, and then you get that result. Okay, that's what you should actually see. Okay. Now in addition to this atomicity, most transactional systems give us what are called ACID properties. Okay? ACID is an acronym that stands for atomicity, consistency, isolation, and durability. Okay? The standard database properties that you get from any transactional system. Atomicity means all or nothing. Okay? Which means in this case, all those 4 instructions should execute or none should execute. You can't have a case where you started executing this code and then you executed the first 2 instructions, then the process crashed. So now your $4 have disappeared. Right? So you can't have things like that happen. Okay? So if that actually happens, you have to make sure that whatever has happened is undone. So you go back to where you were in the beginning, so it looks like nothing has happened. That's your nothing property. Or all of those 4 have to execute, which means the transaction is executed successfully. So you can't have scenarios where half of a transaction executes and then the rest doesn't execute because there's a failure or some such thing. Okay, that's your atomicity property. Consistency says you will take the system from one consistent state to another. So if you started in a consistent state, your database will end in a consistent state. So all the bank balances in this for this account are consistent because that is what is supposed to happen if you are trying to perform these 2 operations. That is an inconsistent state here. Okay, you are gotten into a state that should not have occurred to begin with. Okay, so you're going to get consistency. You're going to get something called isolation, which is also called serializability. Okay, so basically what this says is that the transaction executes as if it's the only thing in the system. Okay, which is the equivalent of saying you got some sort of a global lock. That's not how it will actually execute. But it is given the illusion that there is nothing else executing, so it can make changes and nothing else is changing. That is called isolation or serializability. Serializability also says that even though transactions are executing concurrently, the end result looks like as if they executed one at a time in a serial order, which is what you see here. Okay? In reality, this is not how they will execute. They will still have that interleaving that you had in the previous slide, but you will avoid this inconsistent interleaving. Okay, so but it will look as if they executed sequential. Okay, that's called the isolation property. And durability essentially says once the transaction finishes, it's going to make what is called a commit operation. At that point, the changes are actually stored to disk and there is no way to go back. Okay, so essentially, changes are permanent once the transaction commits. Okay, so most transactional system will give us these so-called ACID properties. So something that you should know. We won't go too much into details of how to implement acidicity here. That's topic for a database class. But what we will do is start talking about how you can have distributed transactions. Okay, any questions on this? Okay, so here is basically transaction primitives. So you will have begin transaction, end transaction. Those are the statements you will write for implementing a transaction. Any code that you write between the begin and the end will get you this ACID property. Okay, you can also abort transaction in the middle, which will undo all of the effects of the transaction. If the code fails or something, the internal system is supposed to do the abort for you implicitly. Right? And then inside the transaction, you can read or write data from your database. Okay? Here's an example. Okay, let's say you want to do an airline reservation. So you want to book a ticket. In this case, the ticket, you are booking a flight that goes from New York to Delhi. Okay, that's an example from the book, but there's no direct flight, so you have to book 3 segments. Okay? So in this case, the ticket reservation is successful if you can book a seat on all 3 segments. If you get 2 out of the 3, you still cannot travel. Okay? So you want all of those 3 things to succeed or nothing. So that is why you are written in this way saying you reserve this first segment. If that first segment says that plane does not have a seat, then you abort the transaction and undo that reservation. If that succeeds, you go and book the next segment. If that works, you do the third one. But if either of those fail, then you go and undo whatever you've done before. So then you will basically get a message saying you cannot make a booking, but you won't have a booking where some seats have been reserved on some segment. Okay, that's how you will write transactional code typically. Any questions here? Okay, so now we can start thinking about distributed transactions, and then we'll see some techniques on how to implement these distributed transactions. So I'll distinguish between what are called nested transactions and distributed transactions, and that is shown in this picture. Okay? Now you can nest transactions one inside the other. Okay? If you have a begin transaction and an end transaction, you can have a smaller transaction in it, which is another begin and an end, so that sub-block within the transaction also executes atomically. Okay? Those things are called nested transactions. And here's an example. Again, going back to our travel example, okay, you have a big transaction. Inside it, you want to make a hotel booking and you want to make an airline booking. Okay? You want the entire reservation to succeed. If both of those things, you can get a flight and you can get a hotel room. If you only get one of those 2, you do not want to travel with that reservation. You try something else. Okay? And in this case, your hotel database and airline database also happen to be distinct databases. So each of them, when you do a booking, you will make a transaction on each of those things. Okay? And then you'll take both of those transactions and nest them on a parent transaction. Okay, so those are your 2 nested transactions. Say, and there's one bigger transaction that encompasses both of them. Okay? This is called nesting transaction. Okay? This is not distributed transactions. Okay? Distributed transactions has similar concepts, but is not exactly that. In a distributed transaction, our database itself is distributed across multiple machines. Okay, so that is what is shown in the picture. Your database where some part of the database is stored on disk of machine 1, some part of the database is stored on disk of machine 2. You get a logical database abstraction, which is this bigger logical disk that looks like it's one big database. Okay? So now you're executing transactions on this distributed database. Internally, the system will have sub-transactions. If that data, the transaction is actually acting on data stored on disk 1, that's your sub-transaction here. There's another sub-transaction there. Okay? So as part of executing a distributed transaction, internally you have sub-transactions that are operating on different parts of your distributed database. Okay? So that's basically the difference. In this case, they're distinct databases and your sub-transactions. They're basically, your database is distributed, so when you execute transactions, you have to implement this internally as sub-transaction. All right. So now we are going to ask some questions as to how do we go about implementing distributed transaction properties and so on. Okay. So I will discuss two techniques for implementing transactions and giving us these asset properties. The first one is called the private workspace model, and the second one is called log-based model. Okay, right-hand log. So let me start with the first one. So in the private workspace model, so you can ask how is it possible to give this all or nothing property. Okay. One way to do it is using what are called private workspaces. The way you can understand this is whenever a transaction starts, let's say you make a copy of their entire database and give it a private copy. Okay, so you make a copy. So now your transaction is not operating on the main database, it's operating on the copy. Okay, so if you have to abort the transaction, it's very simple. You just delete your private copy. The original has not changed at all, so it will look like nothing has happened from an original database perspective. Okay? On the other hand, if you want to commit the transaction, you look at the private copy. Okay? You see what changes were made to that private copy, and you copy the changes over when the transaction completes. At that point, all the data that has changed has actually been moved over to the main database. It becomes visible, and at that point, you can't undo it. Okay? So that's the basic idea behind private workspaces, saying every transaction, whenever a transaction starts, you take a copy of the database and you're going to give that copy to the transaction, and the transaction is going to do all of its work on its local copy, and if it commits, it's going to move the changes. All the writes have to be moved over, copied over. If it aborts, you just delete the private copy and there's nothing to be done. Okay? That's the conceptual idea. Okay, now to implement this efficiently, you're not going to actually make a copy. Okay, with a 10 gigabyte database, you're not going to copy 10 gigabyte just to implement it. That's not going to work. Okay, so what you will do is you will make an efficient copy using a technique called copy on write. Okay, I don't know what to say. Okay, so copying only where it's required. So that is what is shown here. A copy on write. So this is also given an acronym in operating systems. Okay, this is called COP. Okay, which just stands for copy and write. Okay, so copy and write think of copy and write as a lazy copy. Okay? Typical copies that we talk about, we think of it as an eager copy where actually made a real copy. Okay, so if you have 10 gigabyte database, you make a copy where there's another 10 gigabyte use. Okay? When you make copy and write based copies, you basically just have a set of pointers that point to the same set of underlying data. So it's almost like a virtual copy. You didn't make a copy, you just pretended you made a copy. Okay? So long as you are reading data, okay, nothing needs to change because both the original and the new copy are exactly one and the same. The only problem comes if the original has changed or the other one changes. Okay? So that is when you are going to start triggering actual copying, which is why it's called a lazy copy mechanism. You defer making a copy until the last possible minute when the data actually starts diverging between the two copies. But even then, you're not going to make a global copy, only copy blocks as you need them. That is what is shown in this picture. Here you have a disk, the database has 3 blocks. So let's say there are 3 records. We don't really care about blocks here for the example. So there's record 0, record 1, record 2. Here's the index. Okay, the index basically says record 0 is stored at that location on disk 2 here and 1 here. Okay, that's our original database. Okay. We now make a private workspace. In this case, we are not going to actually copy this data. You're just making a copy of the index. Okay? And both of those index and the original are pointing to the same original data, as you can see. Okay? Now, in this private workspace, the transaction essentially goes and modifies record 0. At that point, you are going to make a copy of record 0. Okay, and then you will get your own copy 0 prime, which you are going to change. Okay, the original is still going to point to 0. Okay? So now the private workspace is pointing to some old data and some new data that has been modified. Okay? There is copying on, that is why it's called copy on write. You make an actual copy only when you're trying to write the data. Then you write to that copy. Okay? And then you appended a new record 3, for which you will add a pointer and add a block. The original will not see it, only the private workspace will see it. And now, if you want to abort the transaction, you're simply going to throw this out and delete all the changes, so those blocks will be deleted. If you want to commit, then 0 prime and 3 prime have to be added, okay, by updating the pointers. Okay, so in this case you're committed, so this block pointed to 0 points to the new version of 0, not the old version that's deleted. Okay, and then you added 3. So this basically makes the changes visible in the database. Okay, so that's a simple way how copy and write techniques work. It's an efficient way to make copies of very large objects. Okay, and then they say it's very fast to make these changes. Okay, and then you make changes only when you copy. Yes.
So, do like a database need to be like defragged later because it's moving all the data around and you're
Okay. Question is, should you defragment the data because you are moving it over? In this case, if you have random access, there's no fragmentation. You're accessing fixed size blocks. Okay, the blocks are going to be spread all over disk. Okay? But if you have random access, that's not going to cause a huge performance overhead. You can defragment if you want, but it's not going to give you any benefits in this kind of scenario. Okay, you only need it if you have non-contiguous.
If it's like workspaces in memory or on disk, like because in case of mass writes, it can become an issue.
Okay, question is, are you going to keep this data in memory or on disk? Right, so that's the question. So because this is a database, okay, all the changes are actually reflected on disk. You might have temporary buffers in memory, but because you are getting strict consistency guarantees, okay, if you keep it in memory and you pull the power plug and your machine just shuts down, then you lost all your changes. You don't want to have that happen. So our databases, for correctness reasons, have to do right through, which means that you might keep caches to optimize. And anytime there's a change, you reflect that on disk for consistency purposes. Yeah, that's a performance overhead, but that's the price you pay for correctness.
But only still saying you should keep it like keep your own private workspace on the disk, and while copying, like the copying process fails, something like that. Only it's saying consistency issues.
Okay. The question is, will you see a consistency issues if you're making changes to private workspaces and then something fails during write? If you have a problem while you're making changes to the private workspace, all you do is you will abort the transaction and the whole thing is gone. The original data has not changed at all.
No, actually, it will be other. While you're committing the changes from the private workspace to the database.
Okay, the question is, can you actually have problems if you commit or have problems like power loss during commit? You have to write it in order that where actually it will not have that problem. And you have to be very careful. You may not write necessarily in place. You will first write it up and then you make the change. There are ways to do it which we don't have to go into here now. I mean, that is basically how do you handle correctness in databases. You can actually deal with power failures and so on. You will also have logs, as I'll show you on the next slide, which will take care of that. Okay? Yes.
In this case, we delete the original units and then make the private workspace itself.
Okay, question is, can you make the private workspace the original? You could. It depends on if some other transaction is committed in the meantime, it would have changed this. So you might have to do. Here is only one transaction, so you could have made that. How will you handle it if the original index was? You are just going to apply the changes. So you will basically see which blocks are changed and only change the pointers to those blocks. Okay? The problem comes if someone else modified 0 while you are modifying 0, then you get something called a write-write conflict, and that is handled by databases through locking. Okay? Ideally, you shouldn't get it if you've gotten the right locks to begin with. Okay, any other questions? Yes.
So, while in the case of sub-transactions, how does it work in like 2 commits to like commit the copy?
Okay, how do you handle sub-transactions? So I haven't even come to a distributed database. This concept I'm showing with one disk. So at this point, this is still a single disk system. You have to extend the notion of a private workspace to multiple disks and multiple machines. The commit has to work across multiple machines. We'll come to distributed transaction managers.
Even in the case of a single transaction, we have like the database of the portal and the airline. So both of them are sub-transactions, right? And this one needs to commit only when like both of them.
Okay, question is, how will you, if you have nested transactions, how are you going to make sure that if you commit a sub-transaction, you don't roll it back? So the commit of the sub-transaction and the main transaction all have to happen at the same time. If you commit the sub-transaction while other sub-transactions are going to execute, you can't undo anything. So you will have to commit them all when the main transaction will actually execute and commit. Okay. So the second way to implement transactional system is called write-ahead logs. In this case, we are not going to make a copy of a database. we are going to let the transactions make changes to the main database itself. But we have to have a way to undo the changes if the transaction aborts. Yeah, because if you are in the middle and you want to abort, you want to undo the changes. But you already made changes to the main database. So you have to now keep some extra information that tells you how to undo. And that is called a write-ahead log. Okay? So there is a main database and there's a log file, and the log file is tracking every change you make. Okay? So if you want to undo the transaction, you can then go and see what are the changes this transaction has made. Okay, and then you can undo the effects of those changes. Okay, that's the basic idea. Okay? So your in-place updates, your transactions make changes directly to files. The write-ahead logs is prior to making a change, you have to first write an entry to the log saying such and such changes are being made. That means the transaction ID, the block value, the old value, and the new value have to be saved so that you can undo it by replacing the new value with the old. Okay? And then if you essentially have to commit, you're done. If you want to abort, you read the log and then essentially roll back. And I'm going to show an example of how this works. Okay, so here is a very simple concocted example from the book. So there is two records, X and Y. X and Y are essentially a value of 0. You add 1 to X, you add 2 to Y, and then you set X is to Y is to Y. Okay? So as each of these executes, you're going to keep a log file. And the log file says what record is being changed, what is the old value that was in that record, what is the new value. So if you say X is equal to X plus 1, you'll say X was 0 and I changed it to 1. Okay? That's what happened as a result of executing it. So then when you execute the second instruction, Y goes from 0 to 2. So you write another entry in the log saying I might have modified Y, the old value is 2, the new old value is 0, new value is 2. And then you do the same thing. Now if you want to roll it back, you basically essentially read the log backwards and do a log replay. Log replay simply says I'm going to read backwards and keep undoing whatever has happened. So let's say after you reached here, you want to go back and say, I don't want this transaction to finish, I'll abort it. So then you will say, okay, go change X, the value should be 4, replace it to 1. Okay? Then you say, go change Y, the value is 2, go replace it with 0. Then you say, go change X, value is 1, go change it to 0. Now you restored X and Y back to 0, 0. You're just reading the log backwards and undoing all your changes. Okay? So that's how you're going to make use write-ahead logs. If you have to commit, there's nothing to be done because all the changes are already in place, so you are set. You just write a commit entry to the log that says this transaction is actually committed. Okay, is that clear? All right. So write-ahead log and private workspaces are two approaches, okay, that we are going to keep in mind. Both can be used in distributed transactions. Okay, you can basically keep logs on each disk, or you can essentially use private workspaces of each disk and so on. Okay. But what we are going to now look at is the two by themselves are not enough. We have to have something extra in terms of locks and so on for us to get all our atomicity, acid properties, not acidic properties. Okay. So how do you do that? So this whole approach is called concurrency control. Okay. So essentially you want to have high concurrency in your database. If you say every transaction needs to get a global lock, so only it can make changes, there will never be inconsistency. Because only one transaction is making changes at a time. But your throughput is going to be terrible because all these other queries that are coming to a database will all get queued up. Okay? So what you want is the ability to let multiple transactions all execute concurrently. Okay? And yet, you want it to look like each transaction was the only one that was executing when it finishes. Okay? So you want your correctness property to look like you got a global lock. That's your correctness problem. But you don't actually want to take a global lock because that's going to cause all sorts of problems. So we are going to have to decide how to let multiple transactions execute while still maintaining correctness. In most cases, transactions will operate on different parts of the database. So if your user 1 is making a plane booking to go from, let's say, New York to San Francisco, and user 2 is making a booking from Chicago to Dallas, they are independent flights. They operate on independent rows of the database. There is no conflict between them. They should be able to make changes without any problem. Okay? The problem only comes when you are making changes that are actually going to start touching the same records. Okay? So in most cases, you should actually get the benefits of concurrency. Blocking should only happen when there is actually a conflict between when two transactions are trying to touch the same data. Okay? So how are you going to get your concurrency control is what we are going to look at. Okay? So we'll see how to do this in a layered fashion. Okay? So here is before talking about a technique, I just want to show a picture of how transactional managers work internally. Okay? So there's a transaction manager that's tracking each transaction that's in progress. Every time there's a begin and an end transaction, that request comes to the transaction manager. It tracks that a new transaction has started. It will internally give it an ID, start logging it, or make a private workspace copy. All of that is being done there. Okay. Then there's a scheduler that's actually going to grab locks. And these will be fine-grained locks. You're not going to lock the whole database. You can lock individual records. Okay. Sometimes you can even lock a field of a record. Okay. That's how the database may be implemented internally. So you are going to use fine-grained locks, but not try to globally lock anything. So you have to acquire and release lock, or you can use timestamps as well, as we will see. That's being done as the scheduler, and the data manager is simply reading and writing data. Okay, that's the one. After you've gotten the lock, you're going to simply read and write data, either to the workspace or to the actual database. Okay, that's your high-level architecture, and we'll see how the locking and so on is done to get correctness. But here is the same architecture for a distributed database. Okay? Still one transaction manager, maybe in this case the centralized, but each disk for your distributed database has its own scheduler that's going to lock individual parts of records and fields of that data on that disk. Okay? And the data manager is also simply reading or writing to that disk. And you will have multiple schedulers, multiple data managers. They might talk to one another to figure out what order to get locks and so on. Okay, yes, question.
When you say distributed database, it is a sharded database and not a replicated one.
Okay, question is the distributed database is it sharded or replicated? Sharded simply means you take all the data, you partition it into chunks, and you keep the chunks on different disks. That is what we mean by a distributed database. Replicated database simply means you have 2 copies or n copies of the same database. Okay? We are not talking about replicated databases here. We are talking about actually distributed databases. Okay? Replicated databases also have similar problems, but that's not what we are talking about. Okay? Any other questions here? Okay. All right. So now I'm going to discuss serializability aspects of transactions with a simple example, and then we will try to understand what kinds of read-write conflicts can occur. How can you use concurrency control to implement some of these? Okay, so here there are 3 transactions that are shown here, A, B, and C. Each transaction, actually in this case, all of them are modifying X. It's a toy example. Okay, it's actually a strange example because each transaction first resets the value of X to 0 and then either adds 1, 2, or 3. Okay, and we are going to let all of them execute concurrently. Okay, and then at the end of these 3 transactions, you are going to get some value of X, and you want to make sure that that value is actually a consistent value. Okay. So before you even think about serializability and so on, you have to ask what values of X can you actually accept as correct. Okay. So to ask that question, you could say, let these transactions execute sequentially in some order. Okay. You pick an order and execute them sequentially, and any value of X that results at the end of that execution is a valid value. Okay. So you will say, okay, I'll assume that they execute in the order A, B, C. If that is the case, you'll end up with X is equal to 3, and that's valid. Or you will say, I will execute them as A, C, B. B is the one that goes last. In that case, you'll end up with a value of X equal to 2. And then if you do it some other way, you may end up with X. All of them are valid in this case, because the actual end value depends on which order they executed, because here you are resetting the value. Okay, so now in reality, they will actually get some interleave, but they're all executing concurrently, and this set of instructions here is one interleaving of those 6 instructions. That's the order in which they got interleaved when they executed. Okay, here is another interleaving, here's a third interleaving, and then the question you have to ask is which of them is valid. And so you will see in this case, you end up with X is equal to 3 at the end. You'll say that's valid because there's at least some sequential execution that results in X equal to 3. Okay? In this case, again, you get x is equal to 3. That's also legal. Here you are going to get x is equal to 5. Okay? Because the interleaving essentially executes those two instructions one after the other. So you end up with x equal to 5. And you will say that's not valid because there is no sequential order of those transactions that you can find. You can execute them in any sequential order. There will never be an output that will end up with x equal to 5. Yeah, so if you get that interleaving, you will reject it as being illegal or that there's a right-right conflict, and then you will essentially cause the transactions to abort. Okay, so you want them to execute concurrently, but you want to prevent these cases. These other cases where you have some arbitrary other interleaving, we'll accept as being correct. And there are many other valid interleavings as well. Okay, these are just 3 examples. Okay, is that clear? This is a toy example that demonstrates serializability and when you will accept the inputs and when you won't accept. Okay, so now we will look at how to do concurrency control. So you want to maximize the number of transactions that execute in parallel. That is going to give you high throughput. It will allow the database to serve more clients, okay, and so on. But you want to avoid those problems that will violate serializability because that's an asset property. Yeah, isolation essentially meant serializable. It means no matter how they actually execute, there has to be some sequential order that gives you that end output. And that's what we will accept as being valid. Okay? So how do you do this? Okay? So first approach is basically we are going to say optimistic concurrency control. Okay? So here we are going to be optimistic and say let's not use any locks at all. Okay? We are going to let the database run without any locks. We will assume that most transactions execute and touch the mutually exclusive parts of the database. Okay, some transactions executing some data on some part of the database, other transactions executing on some other non-conflicting aspect of the database. So why do you need locks if they are going to execute and touch different parts of the data? You don't need locks. Okay? So we'll optimistically assume that most transactions actually do not conflict with one another and let them execute without locks. And moreover, when there are problems, we are going to abort the transaction and redo them. Okay? We will track whether there are actually conflicts occurring. And if the conflicts are occurring, we will say, no, you cannot do this. We will have to abort the transaction. Okay? So that's called optimistic concurrency. So inside its conflicts are very rare, so it works well most of the time. And this can be easily implemented using private workspaces. Each transaction gets its own workspace. There are no locks. Okay? When you are going to apply your changes, you see whether somebody else changed the data after you got it. Okay, that was a question that was actually asked earlier. I'm going to go back a few slides. Okay, which said this transaction modified 0, record 0. If after you started, if some other transaction has committed and modified record 0, if you simply overlay those changes, you're overwriting its changes. That's a right-right conflict. At that point, you'll say these two transactions touch the same data, so the second one needs to abort and redo. Okay, but if they touch different records, then there is no problem. You're just letting them execute concurrently. Okay, so this is called optimistic concurrency control. Okay, advantages are it is going to be deadlock free. Is that clear? Why? Okay, there are no locks, so how will you deadlock it? Right, so you're not losing any locks. So there's going to be maximum parallelism, no chance of any deadlocks, okay, and so on. Okay, disadvantage is you might have to rerun the transaction if it ends up with a right-right conflict. Moreover, the problem actually occurs when the load on the system is high. Okay? At low loads, there are few transactions that to begin with, and the probability that they will conflict with one another is low. As the load goes up, there are lots of transactions executing concurrently. So the chances that any two conflict actually go up. Okay? And then you have to rerun that transaction, which means it increases the load even further. Okay? So at high loads, what you see with optimistic concurrency control, the system is very busy executing a lot of transactions. But the good put of the system, and good put is defined to be the number of successful transactions, actually starts falling. Because more and more transactions start conflicting. So that further increases the load, yeah, but then the actual number of successful transactions goes down. Okay, so that's a problem with optimistic concurrency control technique. As a result, many relational databases, if you use MySQL or Oracle or Postgres, which actually use relational database techniques, never use optimistic concurrency control. They actually use locks and so on, which will reduce your concurrency, but they will trade performance for correctness. Okay? Because you don't want a scenario where high load, okay, you are just sitting and waiting with a transaction repeatedly aborts and reruns and aborts and reruns, and nothing seems to be happening in the system. Okay? You're just waiting for it to finish. Okay? So those are all issues that you will see with optimistic concurrency control. Okay? So now I'll talk about pessimistic concurrency control, which means you still want concurrency, but you are going to take a pessimistic view, saying transactions can do bad things, which is they can overwrite one another. So we need to use some locks to prevent this from happening. Okay? In optimistic concurrency control, you took the optimistic view. Bad things won't happen, and if they happen, we'll deal with it after that. Here you are going to prevent them from happening in the first place by actually using locks. Okay? So if you have locks, then you're not going to essentially get any conflicts to begin with. Okay? So in this case, the scheduler part of our transaction system, which I had shown previously, okay, here the scheduler is actually responsible for using locks. In an optimistic concurrency control, this doesn't do anything. There's no locks, but in pessimistic concurrency control, you are essentially going to acquire all the locks, okay, and there are going to be, we'll talk about a particular type of pessimistic concurrency control called two-phase locking. Okay? In two-phase locking, you'll see that there is a growing phase where you keep getting locks, and then you basically execute, and then you release the locks in your shrinking phase. Okay? And we'll talk about how that works in just a moment. So the basic idea is, whenever you try to do an operation on any data item X, okay, you are going to see if you already have a lock. If not, you need to get one. But if it already makes a conflict, then you are going to wait. Okay, meaning that you will wait for the lock to be released. Otherwise, you will get the lock. Okay, and then you have to wait until you are done with X, and only then you are allowed to release it. So inside a transaction, once you have acquired a lock for a data item, okay, you have to wait until you have performed all the operations on the data item before you release it. You can't say, I'll get a lock on X, maybe do read of X, then release the lock on X, then later on when I want to again do some write on X, I get another lock on X. Once you got a lock on X, you have to execute all the transactions, or all the statements rather, that operate on X, only then you are allowed to release the lock for correctness reasons. Okay? That's the rule that you have to follow in two-phase locks, and I'm going to show you an example. Also, the problem with this is going to be deadlocks unless you're careful, but let me show you this picture that shows how two-phase locking works. So in the growing phase, you'll see that you keep getting locks and more data items. Okay? Once you got a lock on any data item, you have to wait until all statements for the data item inside the transactions are finished. Only then you can release the lock. So once you release the lock for, say, X, there should be no more statements that use X for anything in that transaction. Okay? Otherwise, you release it too soon. Okay, that's not going to work. You meaning the scheduler. In this case, the user doesn't do it. So all the job of the scheduler to do this. Okay? So you can essentially start releasing locks once you are done, and then once your transaction finishes, you have released all the locks. Okay? This is called two-phase locking. There's a variant of this which is called strict two-phase locking, where the only thing you do is you wait until the end and release them all at once. Okay? This is much simpler. Keep getting locks, then when the transaction is ended, you release them all at once. Okay? So now, having said this, so you are going to get locks, and once you have a lock, no other transaction can perform any operation on that particular data item because you have the lock on the data item in the database. Okay. Now the problem with this approach is, unless you are careful, deadlocks are going to occur. Okay. This should be very simple to understand. This is the standard way to actually see how deadlocks occur. So if you have two transactions, okay, transaction 1 and transaction 2, then it's a begin transaction, and then you say read of X. Read data item Y from your database. Here you do read of Y, and then do read of X, and then there's maybe more code which I'm going to ignore. Okay? So you will see in this case that if this transaction starts executing, it gets a lock on X, and then maybe that transaction executes and you get a lock on Y. Okay, and then you execute Y here, you will block because you want a lock on Y which T2 holds. And then here you'll go and wait for a lock on X which T1 holds. So you're waiting on one another, you have a deadlock. Okay, that's a very classical example of how deadlock occurs. I hold a lock that some other process wants. That process has a lock that I want. Typically, you'll have a circular weight where each process has a lock that some other process wants, and then there's a cycle. Okay, in this case, this is a cycle of two processes, but it gives you an example of how deadlocks can occur. Yes.
But don't the operations, like after you're done reading, don't you unlock before looking for the lock for the next thing?
Okay. Question is, after the operation completes, do you not release the lock? That is what I said. You cannot actually release the lock until you finished operations on that data item. Perhaps there are more things happening here, saying X plus Y has to be done, something more has to be done. So you can't release the lock here. You will have to release it either at the end or further down. Okay. So what should you do in this case? What is the easiest approach to not have deadlocks in your code?
Acquire everything before you start.
Acquire everything before you start.
Take blocks before each statement and release them just afterwards. So like if you have log on X at line 1, take log on X on line 1, release up before you execute line 2, and like keep going. So like if you have in other lines, if you have it.
So one suggestion is, you have fine-grained locks and release. You can release the lock as soon as you're done with that statement. Now that you can do in arbitrary code, but in this case you're not allowed to, because you said that if you in the acquire phase you can only do acquires, you cannot release. Once you start releasing, you're not allowed to acquire anymore. That's the whole point of the shrinking phase. So you cannot have a case where get a lock on X, release lock on X, then get a lock on Y, because once you release, you cannot, based on this, get any more locks. That's the rule in this case. Okay? So you cannot do that. Okay? Now there's another suggestion saying get all locks at the beginning. Okay? You could certainly do that, but that's not necessarily going to get us very far, because you can say I'm going to get a lock on X, okay, and then a lock on Y. Okay, but after maybe got the first lock on X, this transaction started running, it got a lock on Y, and then it does the same thing. You get a deadlock.
Keep one of the transactions after time.
Can one of the transaction timeout?
After
Okay, so there is, of course, in deadlock detection, you can terminate transactions, but typically if you're holding a lock, there is no timeout. You can hold it for as long as you want. Okay?
the scheduler.
Sorry?
The scheduler.
The scheduler, okay, maybe, but in this case, we are using traditional locks. Okay, so the standard approach to avoid getting deadlocks in your code, okay, is to actually number your resources, okay, and acquire locks in increasing monotonic order. Okay, so you can say I have 10 records. I'm going to order them 1 through 10. In your, so the suggestion what was mentioned was actually correct, which is you want to get all the locks at the beginning, but you want to order also the way in which you get the locks. Okay? So you number the records 1 through n. In this case, there are only 2 data items, so you are going to number them 1 and 2. Okay, these are also going to be numbered the same. So if you need a lock for record 1 and 2, you are going to first get a lock on 1 before you get a lock on 2, because you are going to always acquire lock in monotonic order. So you can do 1, 5, 7, 11. You are not going to do 1, 7 and then get a 5. Okay, if you have gotten 5, then you can only get locks on all other ones. So you basically scan all the statements, look at all the resources you have. Okay, you have ordered all of them in some way, you numbered them, and then if you say I need this set of locks, you basically get them in monotonically increasing order. If you get locks in monotonically increasing order, there's never going to be a case where you hold a lock that somebody, you are waiting for someone else and they hold a lock that you own. And that cannot happen fundamentally. Can you convince yourself why? There's a simple multi-threading concurrency, there's nothing to do with deadlock databases. Okay, so here the problem is you got a lock on 1 and 2. This one got a lock on 2 and 1. That violated that order. Even though you read Y first, then X, that doesn't matter. You should have still got a lock on X before Y based on this rule. That would have caused Y to block and not actually get into deadlock to begin with. Okay? The reason you will have a deadlock is you basically have a scenario where you own a lock on 1, waiting on 2, 2 owns a lock on 3, waiting on 3. 3 owns a lock on 4, and maybe 4 is waiting on 1. This causes a cycle. Okay? If you acquire locks in increasing order, this last thing could never have happened because this process got a lock on 4 and it got it, and then it asked for a lock on 1, which is why it is blocked. It should have asked for 1 and then 4, not 4 and then 1. Okay? That's a simple reason why you cannot actually get a deadlock if you. This has nothing to do with databases. That's just a simple way for you to always reason about your code to understand why it will not have a deadlock and prove to yourself. Okay, so if whenever you have multiple locks in the code, you should, in your mind, order them and make sure every process actually gets them in increasing order if you need those locks, not in arbitrary order. That may or may not work, because sometimes it may get you into a deadlock. This will never get into a deadlock. Okay, you have some question there?
Yeah, is it possible that you break some logic by
Is it possible you can break some logic? If you just acquire all your locks at the beginning and release all the locks at the end, it should not break any logic at all. Because everything else is still the same. It's just getting the locks and then releasing the locks, which is what this two-phase locking will do for us as well. Okay. Yes.
Will it lead to some consistency issues because like if you update X and like you get conflict, will it lead to inconsistency issues?
Question: will it lead to consistency issues? You have locks to avoid getting into consistency problems. If you hold locks on those variables, you should basically be the only one touching that variable. Nobody else can. These are not read-write locks necessarily. You can use them as well, but they are actually normal locks. So ideally, you shouldn't have any problems if you use locks to begin with. Okay, any questions here? Okay, so we went on to a slightly tangential thing just to understand deadlock-free code and so on. But it's important to understand, as you write threaded code, these are all things to keep in mind. Okay, some people in lab 1 thought you needed locks only for your write operation, but not on read. Obviously, that's not true. Right? Anytime you have shared operations, whether they are reads or writes, you need to hold a lock. Okay? If you have multiple locks, you have to also worry about the order in which you acquire them. If you acquire them in arbitrary order, you are going to get into this trouble. You will basically have race conditions, and every once in a while you will get attacked. This doesn't mean deadlock will happen all the time, but if the process is executed in certain order, you will have a deadlock. So you need to make sure you know how to write concurrent code in a proper way. Okay, the first lab actually didn't have too many locks, there was only one, but even there were some issues in how some of you have used the locks to do reading or writing of whatever variables they had. Okay, all right. So let's continue. So we talked about two-phase locking. Then we know how to get rid of deadlocks by ordering them. The last thing I'm going to talk about is yet another pessimistic concurrency control technique, which is not necessarily pessimistic, but it's a timestamp-based concurrency control. We are going to go back to this notion of Lamport's clocks. Okay? Assume that every transaction is an event, and we are going to associate a logical clock with every process. We are going to increment the timestamp, and then whenever multiple transactions try to read or write data, we are going to use logical timestamps to figure out, is that a read-write conflict or a write-write conflict. Read-write conflict says that some other process has already modified the data that I read earlier, so I have an outdated read value. Write-write conflict says some other process came and updated it. I am also going to update it and overwrite its value. Okay? So you want to avoid both of those. Okay? So the basic idea is very simple. Every transaction is going to be given a timestamp, okay, which is our logical clock timestamp. Okay? Now, if a transaction Ti wants to do an operation that is going to conflict with transaction Tj, okay, you are going to abort Ti if you have the lower timestamp, because there's a newer transaction that's come and started making conflicting operations. You are still an older transaction that's still executing. You will abort the old transaction and restart it. Okay, the new transaction will win in this case. The old transactions will abort. So we will abort and restart. Okay, and the way we are going to track whether there is a conflict, okay, how do you know there is a conflict, is for every value in your database, you will keep the last read time and the last update time. Okay? So which is what these things say. So this is the maximum timestamp of a transaction that read X, which simply means the most recent transaction that has read X. this says this is the most recent transaction that has read or written to X. So you have a read time and a write time for each value in your database. Okay. Now, if you do this, you basically just do this very simple thing to figure out if you have a conflict. Okay. You will take, if you are a transaction Ti and you are trying to read value of X, you will say if the read of the timestamp of the transaction is less than the max write timestamp. That means there's already a newer timestamp that went and wrote it, and that's the value that's reflected for X. Then you are an older transaction, you are going to be abort. As I said, if you have a conflict, then the newer transaction wins. You have a newer transaction with a later timestamp has already gone and returned to X. You have newer older transaction that's trying to read X, so you will get abort. Okay. The same thing happens. Otherwise, you'll perform the read and then update the timestamp. Okay. And now in the write case, you are going to check if the transaction timestamp is less than the read timestamp or the write timestamp, which means a newer transaction has either read or written, so you will basically abort. It's the same concept again is being used. Otherwise, you perform the value of write and then update the value of the write timestamp. Okay. So in this case, you're not actually using locks, but you're simply checking which transactions are read or written to what parts of your database. And you always let, whenever there's a conflict, you let the new transaction win. The old transaction aborts, undoes it, changes, and then you restart it. Okay, so this ensures that you go and trample over one another's changes. Okay, so this is using logical clocks and timestamps to reason about what has actually happened in your database and how can you ensure that there are no conflicts. Okay, there's a picture here which I'm going to ignore, but that's in the book, which shows some examples with this. Okay. So if there are no questions, I will end the class today. Okay, we will have no makeup. There's a schedule shows a makeup class on Friday, but last week I mentioned that I cannot hold that class. I'm going to reschedule it. Okay, so there is no makeup class on Friday. We'll have a regular lecture on Monday. And you already know I extended the lab to deadline to next Tuesday. Okay, so let's stop here today.